2.4 Lesson 1, Continuity and Discontinuity. Our objectives for today's lesson are: 1. You will know what a one-sided limit is. So we've actually seen this already, but we'll take another look at it. It's the same thing, just a review. You will know the three ways in which a function may fail to be continuous at a point. So we'll look at three different ways in which a function will be discontinuous at a point. And then we'll make sure none of those three things happen. And we'll use that to look at the definition of continuity of a function at a point and on an interval. You'll know the difference between two types of discontinuity. One is removable and the other is non-removable. Vocabulary, as we've seen before: one-sided limit, left-sided limit, and right-sided limit. And new vocabulary, we've been using this term, but we haven't defined it formally. So today we'll look at the formal definition of continuity. And then you can have two different types of discontinuity: removable or non-removable. And so if you have a step discontinuity or an infinite discontinuity, that would be non-removable. And we'll take a look at examples for each one of them. But let's take a look at what a one-sided limit is. We'll begin by reviewing that. So here we're taking a look at the graph of a piecewise defined function. F of x is equal to x squared for x values that are less than or equal to 1. And you can see the red part of the graph. For domain values that are less than or equal to 1, we have the graph of this parabola, but it stops at x is equal to 1. And for domain values, for values from the domain that are greater than 1, we use the rule negative x plus 3, but only for values of x that are greater than 1. So you can see that the green graph, it starts at 1 with an open circle, and then you have the rest of it to the right of x is equal to 1. Now let's think about the limit of f of x as x approaches 1. If you think the limit does not exist, you're correct, because if x is approaching 1 from values that are smaller than 1, you can look at the red part of the graph and you can see that the y values are approaching 1. But on the other hand, if x is approaching 1 from values that are greater than 1, you can look at the green part of the graph and you can see that the output values of the function are approaching 2. So when the input values get closer and closer to 1, the output values are not getting closer and closer to a single number. They're getting closer and closer to two different numbers. So the two-sided limit does not exist. However, the one-sided limits do exist. So in a one-sided limit, you just consider what's going on as x approaches 1 only from one direction. So for example, if x is approaching 1 from just the left of 1, you use that superscript of a minus sign. So if the input values are getting closer and closer to 1 from the left of 1, the output values are getting closer and closer to positive 1. So the left-sided limit is 1. And we can also look at the right-sided limit of the function f of x. So you would write the limit of f of x as x approaches 1 from the right of 1. And you use that superscript of a plus sign. This means the input values are approaching 1 from the right side of 1. And when that happens, you can see that the output values of the function are approaching 2. So the one-sided limits exist, but they're not equal to each other. And for the two-sided limit to exist, it is necessary that the one-sided limits exist and equal each other. So what we just went over now is stated as a property in your textbook. Property, one-sided limits. And here we have the limit of f of x as x approaches c from the left. And here we have the limit of f of x as x approaches c from the right. And here we have the statement that we went over, that the two-sided limit would exist and equal L if and only if the left-sided limit and the right-sided limit both exist and they're both equal to the same value, L. And if that's the case, the two-sided limit will exist. In our example, the one-sided limits existed, but they equaled different values, and therefore the two-sided limit did not exist. So we just looked at one-sided limits, and we used vocabulary. And now we're going to look at objective 2. You will know the 3 ways in which a function may fail to be continuous at a point, and that will lead us to objective 3, in which we basically say, let's make sure none of those 3 things happen, and we define what we mean by continuity of a function at a point and on an interval. Before we discuss what's on the screen now, we would like to just have a short discussion about what we think of when we hear the word continuous or continuity. To be continuous means that there is no gap or break or some kind of a pause. There is a smooth continuation. So for example, you might say the continuity of government, which means there is no gap or break, but there is a smooth transition from one government to another, from one administration to another, so on and so forth. Discontinuity means there is some kind of a break. So if you look at these 3 graphs here, you can see that there is a discontinuity for the first graph because it may be a little bit hard for you to see, so I'm going to go ahead and zoom in there. So for figure H, you can see that there is what we call a discontinuity. There is a gap in the graph. Before we talk about why it's removable, let's just keep it simple for now. There is a discontinuity. And the reason why there is a discontinuity is because the graph has a hole or a gap. In other words, the function f that whose graph we're looking at here, is not defined at the input value c. So why is this not continuous at x is equal to c? Because the function f does not have an output value defined for the input value c. So I just wrote what I said in 2 different ways. And let's take a look at our second graph. You can also see that there is a discontinuity here. There is a gap in the graph. But the gap in the graph for the second figure I, occurs for a different reason. You can see that if you look at this part of the graph, you can see that there is a solid circle there, which means the function f is defined at x is equal to c. And in fact, from the graph that we're looking at, we know that the function f evaluated at c would be equal to 7. So we have a discontinuity in the second figure, but for a different reason than what we saw in the first figure. It's not because the function is not defined at c. The function is defined at c. But what's going on? The limit of the function as x approaches c does not exist. Why not? The left-sided limit is 4, and the right-sided limit would be 7. And because the 2 one-sided limits do not agree with each other, the two-sided limit does not exist. So that is the reason why we have discontinuity for the second figure. Now let's look at the third figure. You can clearly see that the graph has a gap at x is equal to c. So there is a break in continuity. So we definitely have a discontinuity. But the discontinuity occurs for reasons that are different from what we looked at earlier. So unlike the first situation, the function is defined at x is equal to c, and you can see that to be the case because the graph has this particular point on it. So when the input is c, there is an output value assigned to the input c. So the function is defined. So it's discontinuous, but not for the first reason. Furthermore, the function does have a limit as x approaches c. So if x is approaching c from the left of c, or if x is approaching c from the right of c, the output values are approaching L. So the limit of f of x as x approaches c is equal to L. So we do have a discontinuity, but as we saw earlier, it's not for the first reason, and as we just saw now, it's not for the second reason. So how can we describe why we have discontinuity for the third figure? We can describe it in this way. So the limit of the function as x approaches c is equal to L, so the limit exists, but the output value of the function at x is equal to c is not equal to L. It's equal to something else. So that's why we have discontinuity in the third case. So we will say the limit of f of x as x approaches c does exist, but it is not equal to the output value of the function at c. So these are the three ways in which a function can fail to be continuous at a particular point x is equal to c. So now we will look at the definition of continuity, which basically states, let's make sure none of these three things happen. So here we have the definition of continuity from your textbook. So continuity at a point. Function f is continuous at x is equal to c if and only if these three things that we just saw don't happen. So in condition number one, we say this here cannot happen. So we say that f of c must exist. So why is it that we had discontinuity in the first example? Because f of c was not defined. So now we say f of c must be defined so that the first situation doesn't happen. Why is it that we had discontinuity in the second situation? Because the limit of the function as x approaches c did not exist. So we're going to require that the limit of the function as x approaches c must exist so that the second situation does not happen. Why is it that we had discontinuity in the third example? The limit of the function as x approaches c did exist. The function was defined at x is equal to c, but their values were not equal to each other. So we want to make sure that doesn't happen. So we say the limit of f of x as x approaches c must be equal to the function's output value at c. So when we state that, we're making sure that the third situation does not happen. So if we have all three of these conditions, we have continuity at a point, at the point x is equal to c. What does it mean for a function to be continuous on an interval? Function f is continuous on an interval of x values if and only if it is continuous at each value of x in that interval. So if we can show that this is true for all x values in a particular interval, then we can conclude that the function is continuous for all x for that interval. At the endpoints of a closed interval, for example, if you're considering the interval from 1 to 5, so the endpoints would be 1 and 5. So you would only be able to approach 5 from the left of 5, and you would only be able to approach 1 from the right of 1. And at the end points of a closed interval, only one-sided limits need to equal the function value. So we have continuity at a point and continuity on an interval. So we just looked at three ways in which a function may fail to be continuous at a point. And we looked at the definition of continuity of a function at a point and on an interval. Basically, in the definition of continuity of a function at a point, we're making sure that none of these three things would happen. So now we want to take a look at objective 4. You will know the difference between a removable and a non-removable discontinuity. So let's review some vocabulary. We already saw one-sided, left-sided, and right-sided limits. We looked at continuity, and now we're going to take a look at objective 4. You will know the difference between a removable and a non-removable discontinuity. So a discontinuity can be one of two major types, either removable or non-removable. And under the non-removable branch, you could have what's called a step discontinuity or an infinite discontinuity. So going back to the definition of continuity, we know that for a function to be continuous at a point, these three conditions have to be satisfied. If conditions 1 and 3 are not satisfied, then you will have discontinuity. Which of the pictures that we're looking at correspond to conditions 1 and 3 not being satisfied? Well, in condition 1, it is required that the function be defined at x is equal to c. So here, we don't have the function defined at x is equal to c. And condition 3 requires that the limit of the function as x approaches c would be equal to the output value of the function at x is equal to c. So let me use a different color. And here we see that this particular condition is not satisfied for the second graph. So we have discontinuity, but those are easy to fix. They are removable. Why are these removable discontinuities? So if you have a discontinuity because one of these two conditions are not satisfied, that's easy to fix. So if the first condition is not satisfied, resulting in a discontinuity, how do you fix it? You just go ahead and say, all right, I see that f of c is not defined, so I'm just going to define it. I'm going to say, let f of c be equal to L. So that gap is filled, and you now have continuity, and your discontinuity has been removed. What about the third condition? If the third condition is not satisfied, that's also very easy to fix. What's the problem? The problem is the limit exists, and the function is defined at c, but they're not equal to each other. So how do you fix that? Well, let's just make them equal to each other. So you just redefine f of c to be L. So get rid of this point and put it over here. And now the discontinuity has been removed. So if you want to sort of relate it to something from real life, just for the sake of helping you remember or understand the difference between a removable discontinuity and a non-removable discontinuity, imagine that you go to buy a goldfish and you go totally unprepared, so you put your goldfish in a Ziploc bag with water. And as you're walking home, unfortunately, you drop the Ziploc bag. But if you're lucky, maybe nothing will happen, or maybe it'll hit something sharp on the ground and there will be like water leaking from one particular spot. Well, that's something that you can fix pretty easily. Maybe you just kind of like hold your thumb against it and you fix the problem. But if you're really unlucky, you drop the Ziploc bag and maybe the Ziploc bag like breaks. What are you going to do? There isn't much you can do. It's like a non-removable discontinuity in that case. So let's take a look at when we might have a non-removable discontinuity. So we're going to have a non-removable discontinuity when the second condition from the definition of limit is not satisfied. That would result in a non-removable discontinuity. So if you have this type of discontinuity, you can't fix it. It's called non-removable. So when does that happen? When the limit of the function as x approaches c does not exist. And that's taking place here in this third figure. We have a step discontinuity. In a step discontinuity, we have the limit of f of x as x approaches c from the left. It exists, but it is not equal to the limit of f of x as x approaches c from the right. If that's the case, you would have a situation like this. That is a non-removable discontinuity. It's called a step discontinuity. So we just looked at removable discontinuity, and we looked at one type of a non-removable discontinuity, a step discontinuity, and now we'll take a look at a second type of a non-removable discontinuity, an infinite discontinuity. An infinite discontinuity is a type of non-removable discontinuity. One type of non-removable discontinuity is step discontinuity, and a second type of non-removable discontinuity is an infinite discontinuity. They both happen for the same reason. The second condition from the definition of limit is not satisfied. So the limit of f of x as x approaches c does not exist. In the case of a step discontinuity, the two one-sided limits exist but are not equal to each other, in the case of an infinite discontinuity, one of the two one-sided limits may not exist, or both of them may not exist. So what's going on here? As x approaches c from the left of c, the output values do not approach a single number, but they just increase without bound. So the output values go to infinity. You can also see that as x approaches c from the right of c, the output values of the function do not approach a single number, so the limit does not exist. In fact, the output values increase without bound. The output values are going to infinity. So we call that an infinite discontinuity, and we'll see more of that in the next section. So we looked at continuity and two different types of discontinuity today. Take a look at just the last two figures here. The functions that are represented by the graphs shown in the last two figures are continuous at x is equal to c, because all three of these conditions from the definition of continuity are satisfied. So, for example, here, the function is defined at x is equal to c. The limit of the function as x approaches c does exist, and the limit of the function as x approaches c is equal to the value of the function at c. So we have continuity for the figure here, but there's like a sharp corner at x is equal to c, but that's okay for continuity. And here, for the sixth figure, we have continuity as well, but that seems pretty obvious. It's just like what we were talking about before. So we just saw an example of an infinite discontinuity. So today we looked at our objectives. You now know what a one-sided limit is. We know the definition of continuity, and we know the difference between a removable and a non-removable discontinuity. And we looked at Objective 2 prior to looking at Objective 3, and we looked at our vocabulary terms.